Let's begin our session of today. We'll start with special relativity given by Einstein. Special relativity. Okay. So this special relativity was a path-breaking paper given by Einstein, and this made him worldwide famous. So let's start. According to Newton's first law, we know that a body is in a state of inertia. Okay. Now what is inertia? Inertia is a state when there is no force acting on it, either no force acting on it or the body is moving in constant velocity. In other words, inertia is a state when the acceleration is either zero or velocity is constant. Okay, so let's imagine, let's say we have a car. Okay, we have a car, and here is sitting Mr. Einstein. Okay, and this car is moving with velocity v on a flat road. If it moves with velocity v, after some time Einstein will reach here on his car. But will it be moving for Einstein? Let's say we have this man. This man E is moving with velocity v, and we have the car 2 which is moving with v. So with relative to each other, will they be at constant velocity? No, they will be at rest. Let's say ve minus vc, let's call this c, is equal to 0, because both of them are moving with velocity v. Since ve is equal to vc is equal to v, hence ve minus vc would be 0. But let's say we have an observer here. Okay, this is the car. Mr. Einstein is sitting on it, traveling with velocity v. And here is an observer who is standing on ground. He has no velocity, he has velocity 0. After some time, when Einstein will reach here, for him, Mr. Einstein has moved. Let's say it took time delta t. Then this distance traversed, which be equal to v into delta t. We know what? The distance is equal to speed into time, and this is how we get our derivation. But let's say for Mr. Einstein over here, what will he say? He will say, I am at rest because I am inside the car. But for me, this person has moved. Got my point? Let's say there are two trains. Okay, two trains. Both of them are moving with velocity v. And you are sleeping in the train. When you wake up and you look from the window, you will see the train to be at rest because both of them are traveling with velocity v. Let's think of another situation. You are inside the train. This is the train, and now you just woke up and you found the train you are looking from the window is moving backwards with velocity v. Can you guess that either you are at rest or this train is moving? Or it may be possible that this velocity is at rest while you are moving. So this is the trivial problem with the relativity, when we cannot determine that whether we are at rest or at constant velocity. So this was first discussed thoroughly by Einstein. He said we cannot determine whether I am moving, or the objects are moving. Okay. So this person sitting inside the car looks at outside. His car is moving at velocity v, and we have a coconut tree here. What this person will say? He will say, I am at rest, but this coconut tree is moving to me with velocity v. This is the whole idea of inertia, where there is no acceleration or the velocity is constant. Okay, got my point? Now, let's imagine there is Einstein, okay, in the car, standing, and he throws a ball up, okay, and this ball comes down after time t, okay, and he catches the ball. But for the person standing on the ground with zero velocity, he will see that the ball is traversing in a space, okay, and this took time x, and the ball rose up from here and then it fell down. But for Einstein, who is standing upright on the car, he will see no such difference. Because when he threw the ball up, it was in a state of constant velocity v, and after time t, it will come back at him by the time the car would have moved like this, isn't it? And it will come back to him. So it is the game of inertia. Okay. So how do we conclusively say that whether we are at rest or we are moving, or the world around us is at rest or moving? We cannot say. So for this, we need to verify it experimentally, and this is what was done. So whatever object Einstein threw from the car, okay, let's say he threw an object with velocity v, but the car was already with velocity v. So before he threw the object was already in velocity v, hence the resultant velocity would be v plus v equal to 2v. Getting my point? So Einstein was in a great problem. So this was a thought experiment that he ran. Uh, Firstly, he threw the ball vertically, then horizontally. Both of the time, he couldn't determine whether he is at rest or he is moving, or the world around him is at rest or is it moving. Okay. So next time, what he did was he imagined. Let's say I throw a wave instead of an object, because objects have inertia. Waves don't have inertia. Waves do not depend on the inertia because they depend on the property of the object. Okay, so Einstein imagined, let's say the car is moving with velocity v and I throw a sound wave from here. Let's say the sound wave is at velocity v. So now for Einstein, it will seem that the car and the sound wave both have freezed, isn't it? Because both of them are moving with velocity v. This is the sound wave, Einstein standing up. So for him, both of them will be at freeze. But we know that sound waves do not travel in vacuum. It needs a medium, and here the medium is air. So Einstein postulated, no, the sound wave for me is static, but it is due to the air pressure exerted on it from the opposite side. So maybe sound waves are at rest due to the pressure from the opposite side by the air, or the force exerted by the air. So maybe for this reason, the sound wave and the velocity of the car is at zero. Okay. So next he thought, no, this cannot be done. So let's change the wave. And he chose light. Okay. Light is a part of electromagnetic spectrum, and these electromagnetic spectrum do not need any medium. Earlier, it was hypothesized that light waves travel through a medium called ether, but this kind of thoughts were falsified by Michelson and Morley experiment, where they established that light travels with constant speed is equal to 3 into 10 to the power 8 meter per second, and it doesn't need any ether. So this ether theory was falsified. So now Einstein knew that if I choose light instead of sound waves, so let's say he's up in the car and he's throwing light wave with velocity c, and he somehow travels with velocity c. Now what will happen? Will he ever come to the conclusion that whether the car is moving or he is moving? So let's say here is an observer standing on the ground, and he is at velocity 0, he is at rest. So for him, both of them will move with velocity c. So this is the extent of relativity. Here the Newtonian relativity collapses, and both of them, the car as well as the speed of light, will move with velocity of 3 into 10 to the power 8 meter per second, and both will travel through speed of light. It will look something like this. We have seen this scene in the Star Wars, isn't it? Okay, got my point? Let's come back to the most important topic. So we will discuss here about a very important concept here, which is called time dilation. Okay, let's say instead of having a normal clock, we have a light clock. What is a light clock? We have light traveling with speed of light and a distance L. When this light goes to the other part, let's say it starts from point 1 to point 2. When this light travels from point 1 to point 2, we count it as 1 second. Okay, so let's call this as light watch. Okay, or light clock, whatever you want to say. Light clock. So for a person standing with velocity 0, let's say light clock has a distance of L, and this traverses the distance. And let's say there is a moving object, okay, traversing with velocity v, and from here the light is going there, because by that time t has traversed and the light has reached over here. Getting my point? With velocity c, and this length we call it as L dash or L prime. So distance L, and for this person standing as static, let's call him static, so ts. Okay, for this person relative to the object moving with velocity v, how it will look? It will look something like this, L prime. So let's have uh, ts divided by tm. Tm is for the time taken on uh, this part. Okay, so tm is for the person looking from here. For him, the object has gone up, the light for here, the light has gone up and has come down. Okay, and it took time t. But for this man, static over here, according to him, the object went something like this and then came back. So ts for the person standing static, ts would be equivalent to L prime, and tm will be equivalent to L, where ts is time with respect to the person standing and tm is equal to time with respect to the person moving with velocity v. Okay, so let's do it. So we have this L prime, sorry, L prime. Okay, and we know that this distance is L, and since for the person looking at velocity v, this would be ts, because for him he's observing the whole experiment. So for him the object was already moving with velocity v, so the distance would be v into ts. Got my point? Now if we use simple Pythagoras theorem, we will know L prime square is equal to L square plus v into ts square. Okay, then we will have L square is equal to L prime square minus v square into ts square. Got my point? Let's call it delta ts for our own convenience. Okay, got my point? Now, L square is equal to L prime square. What is this L prime? This was the speed of light because it was a light clock. Light was moving and it took time ts. So we will write here as C into ts square, okay, minus v square into delta ts square, okay. Now L would be equal to, let's equate on each side, ts on the root c square minus v square, and by this way we can say L prime by L would be is equal to, just now we calculated what, L prime is equal to speed of light into delta ts. So here it will be c into delta ts divided by delta ts, okay, delta ts c square minus v square, okay. Now if we cancel this and if we divide both of them by c, then we will find L prime by L is equal to 1 minus square root of 1 minus v square by c square. So this is the main objective to be found here. So how we started? We started with Ts divided by Tm, where Ts was time with respect to the static observer, whereas Tm was time for the moving observer. Ts was, let's write elaborately. Ts is time for the static observer and Tm is time for the moving observer. Okay. Now, so how we will write? Ts del Ts by del Tm is equal to L prime by Lm is equal to 1 minus square by c square. So this thing is called gamma factor. Okay. So now what we can write? If we look from here, we can easily write that del Ts is equal to 1 by 1 minus v square by c square into del Tm. What does it say? So for the static observer who is looking at this whole event, okay, for the static observer who is looking at this whole event, his time is equal to gamma factor into the time of the moving observer. We know that this gamma will be always greater than 1, okay, since v is smaller than c, hence the v will be more than 0 and less than c. So this is how we evaluate the gamma factor. So what does it say? It says that time will be different for these two people, okay. So one person who is standing static will look at the whole event. One person who is standing static will look at the whole event. For him, the time will be more, isn't it, for this whole event to occur? Whereas for the person sitting inside this system, for him time will be different. So for both people time are different. So for this static observer time ts and for this moving observer time is equal to tm. Okay. So here is a computer simulation. Okay, I found this interesting website where we can run the simulation. Just now, what did we see? We saw the time for the static observer is equal to gamma factor into the time for the moving observer. And we got a very interesting equation where we had square root inside 1 minus v square by c square. So let's say here the velocity of the we have velocity of the object which was moving with velocity v, and that velocity is infinitesimally smaller than the speed of light. Let's say the velocity is 10 kilometers per second, whereas we have light is equal to 3 to 10 to the power 8 meters per second. So if in such situation, let's run a simulation where the velocity is very negligible comparing to the speed of light. So let's run. You can see both the clocks. Here we have called Jack and Jill. Jack is the observer who is static, and Jill is the observer who is moving with velocity v. Okay, you can see both of them traverse with the here we have 8 second. Okay, because the velocity of Jill is way smaller than speed of light. Let's run it again. Okay, v is very small comparing to the speed of light. Hence, the clocks of both Jack and Jill show very similar time. Okay, got my point? Now, let's say we wanna do this experiment and we wanna increase the velocity. And this velocity now, let's say we took it to half of the speed of light. Let's see how it goes. Okay. Now the velocity of Jill, who is moving inside the car. Okay, earlier we used to call it Mr. Einstein. Let's call him Jill now. Okay, so for Jill, who is moving with velocity v, the v is half of the velocity of the speed of light. Let's see how the clocks behave now. Okay, see, see, for Jack, he has to traverse more time. Look, 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 look. The time has now slowed down. For Jill, you can see for the same distance, Jill's clock reads 8 seconds, whereas Jack's clock reads 9.21 seconds. See, earlier it was 8 seconds for both, but now for Jill, who is moving with velocity half than the speed of light, for her the time has slowed down. Let's do it again. Let's do it again. We have velocity v is equal to half of the speed of light. Let's do it again. You can see for Jack it was like just like earlier. It's a normal clock. He's not moving. He's static. But for Jill, who is moving with velocity half than the speed of light, for her time has slowed down. See, the reading shows Jack's clock reads 9.21 second, whereas Jill's clock reads 8 second. Let's increase the time further. We have increased it to around 0.75. Now, the velocity with which the Jill's car was moving is 3/4 of the velocity of speed of light. And now we run the simulation again. Let's see how it happens. Look, the time has further slowed down for Jill. See, time has slowed down so much for Jill. So we can say, so in Jill's clock, let's finish the experiment first. Okay. See, when the light went from here and reflected back, Jill's clock read 8 second, and the Jack's clock read it 12.18 second. What does it mean? The time slows down when we move comparable to the speed of light. So this is the whole concept of time dilation. I hope you understood with this example. Let's run this simulation again. See, since Jill's car is traversing with the speed of light, 3/4 to the speed of light, hence for her the time has slowed down. Whereas for a static observer who is not moving, the time seems faster. So this is the whole paradox. Got my point? Okay, thank you.